Invite the second keynote speaker, Dr. Mohamed Elhoseiny. Please welcome him. He's an associate professor of computer science at KAUST and a senior member of both IEEE and AAAI. He earned his PhD from Rutgers in 2016 and has held research appointments at Stanford, Baidu, Facebook AI, SRI International, and Adobe Research. His work focuses on efficient multimodal learning under limited data regimes, particularly zero-shot and few-shot learning in computer vision. He has won NSF Fellowship, CVPR Doctoral Consortium Award, and ECC Best Paper Award, and had been featured at United Nations, MIT Tech Review, HBO Silicon Valley, and Forbes Science. So now I'll hand it over to him.
Thanks for the nice introduction. And, I'm excited to be here. Today, I'd like to share with you today some of the work we have been doing towards scalable and structured understanding of video LLMs. So this is the agenda. I will start first by some background on image LLMs and image LLMs. So my connection to this field of image and language has dated back towards 2013, where we introduced this problem of recognition of unseen species based on language. So if maybe most of us may not know what parkiroculid is, but if we describe that in language and say that this is a bird that has a short orange beak and the plumage is dark above and white below, it's easy for us to imagine how this bird looks like. And it becomes easy for us to identify this specific bird among these different ones. And this from the formulation that we had back then in 2013 was based on contrastive language and image training on seeing classes, and then we generalize that on unseen classes. And the idea is basically pick image text pairs, and those that belong to the same class, make them similar, and those that should not belong to don't belong to the same class, make them least similar. Increase the distance as much as we can. This relates to what we refer to today as contrastive language and image pre-training. It's basically the same idea, but the difference is that the CLIP is based on deep learning. The deep visual encoder, the image encoder is deep, and the language encoder is deep, and the training has happened is much larger amount of data. So I wrote a blog post here that summarizes a decade journey in this space, but the key idea is that the image and language pre-training have shown a lot of success when scaled on large amount of data and deeper architectures. When we look at this today with today's vision LLMs, we think that this can also be scaled to much larger number of species. So this is a paper we put on arXiv recently that scale recognition to more than 10,000 bird species. In this case, you have a repository of more than 10,000 birds, and as well as their images. And in addition to using CLIP architecture, we augment that with a RAG-based system. So you can see here, CLIP doesn't perform very well, but when augmented with recent vision LLMs in a way that is aware of these species that we want to distinguish and tell them apart from each other, the performance increases significantly by almost double. Getting back to how the journey of connecting vision and LLM has started, our first work in this space was VisualGPT that was released. We published at CVPR, and the idea was at that time was VisualGPT was based on VisualGPT on GPT-2 by OpenAI, and basically we feed the images into a stacked transformer layers, and this is together learned with a learnable cross attention mechanism that bridges the visual information into the large language model to enable image captioning. At that time, this was basically the first work that integrates pre-trained LLMs for facilitating image captioning. This enables it to perform quite well on limited amount of data. As you can see here, VisualGPT enabled the model to perform with only a few thousand examples on medical report generation to perform at a CIDR score of 49% compared to 27% at that time. These models up until this point was not instructable. So later, a family of like vision language models has been introduced, including MiniGPT, concurrent work with Elava, visual instructing tuning. This was released in April 2023, and the point here is to bridge the gap between large language model as we know today post ChatGPT, so that we can instruct it to do some tasks that was not possible before. For example, you can ask the model to find the problem with this plant and then guide you to how do you fix it, or give it a picture of your meal today and ask it how can you make this meal at home, and so on. So this become more possible with today's large language models because of their ability to their increasing ability to understand visual content, language content better, and pre-trained knowledge like writing advertisement, as well as, for example, writing poems, can be bridged pretty efficiently with limited amount of image text pairs to enable these kind of tasks. So this spent some time, last some time to be performing well on the next few months, whereas later lots of great work based on Elava that has also done a lot of great progress following on that. The key idea for this was to limit the amount of learning that is needed to bridge these gaps. In this case, on the extreme, the LLM was completely frozen with one linear layer that connects the image to the large language model. And this has happened with two training stages. One is based on image short text pairs. That was not sufficient at that time to have a model that can produce large text that is ChatGPT-like. And this has to be corrected later by a second stage of visual instruction tuning, which happens to be very efficient. It requires only several minutes for training. All right. So later we have introduced the MiniGPT, a second version of this, which enables like grounding. So in this this model can enable, for example, if you describe this image in detail, ask it to describe this image in detail, it will tell you that this image has two cups that are stacked on top of each other. There's some technical issue. All right. So it will tell you, for example, where each cup is, which ones are pointing up and pointing down. This kind of ability is quite important, especially when we wanted to understand the physical world, and in connecting it to video understanding is something that I think is like a lot of progress, and there's a lot of more work needs to be done to address this need. More recently, we developed the MiniGPT video, which we later integrated with the Goldfish paper, which is a video language model that can process few minutes videos. So you can give it a video like, not sure if the voice is. And the idea of this work was based on embedding the images with VIT image encoder and pass us through a linear layer, and then with some sort of downsampling to decrease to compress the visual information per frame, and then feed that visual information together with subtitles into the large language model to enable the prediction. Later, it becomes essential for us to think about how to process longer videos. What we mean by this is how we process hours of videos. And this leads to the next section of the presentation. Goldfish is one of the works that we introduced last year at ECCV. And the idea behind that is to integrate video LLMs with RAG-based model to identify the clips that are most relevant to the video. So, for example, here when you ask the model, what does Phoebe show Monica when you were talking, the model will go and find the relevant clips that are relevant to the question, and then.
Well, look no further. This one's yours.
All right. The way this works is based on having a retrieval mechanism that, given the questions, ranks the videos, the video clips. So we segment the original long video, like it could be hours or something, into clips. Each one is 16 seconds. And then we process this through the MiniGPT video that we just described to produce a language description of each one of those short clips. And then, given a query, we then compute the language similarity between the query and each one of the language descriptions of these short clips, and then find those that are most relevant, and then go get this the most relevant top K clips, and then feed it to the large language model to process it and come up with an answer. So this is the key idea of Goldfish. At that time, compared to the available video LLMs, it performs quite well. And when you include the subtitles, it can also do better. This is on standard short video understanding benchmarks. This one is on long video understanding benchmark. In the benchmark we propose called TVQA long, which is based on TV shows. And the performance here if you access only video information, the performance is much better than baselines at that time. And you can see here that also the model accuracy is consistent. It's just like it's consistent across the shorter videos and also longer videos, where other model struggles as the duration of the video gets longer. Now I get to LongVU, the model we in collaboration with Meta on spatial temporal adaptive compression for long video understanding. The key idea here is that the current challenge in multimodal models is that the visual information is huge and it's hard to manage. 20 minutes video, even at 1 frame per second, is about 172,000 tokens. And if you think about 1 day of video, this is more than 12 million parameters. And this if you imagine if you want to process like Netflix or Prime Video or something like that, this is not manageable. So the way we can do that, we want some mechanism that can gather information, that can compress information more efficiently. And in LongVU, we did some effort motivated by that, to compress the information in the video so that large language model can operate on it more efficiently. So the way we do that is that instead of uniform sampling or dense sampling, where we have to truncate or also discuss some information in a way that is not temporally aware or not motion aware, we do that in a little bit adaptive way. So first we do reduce the redundancy by dyno prior. So we compute the dyno features for all the images, and then we compute the similarity between every frame and all other frames. And we drop the frames that have high similarity to all other frames. So we truncate this from N frames to T frames, where T is much smaller than N. And then second, after that, we feed this. We borrow the idea from Cambrian, which has been proposed in the image domain, to combine signal feature and dyno features into and feed us through a special vision aggregator, which is the mechanism was proposed in Cambrian paper. After that, and based on the idea that visual information in specific locations in the videos might be fixed along the video. So right now, as I'm speaking, most of the background does not move. So basically, the idea behind that is to look at a specific region temporally, and if this region does not change over time, I keep one copy of this and neglect all the others. For regions that change a lot, I will keep all the information. And this can reduce. You can see the figure this figure, for example, shows how much reduction has been achieved by the first step, which is the dyno prior. And this step shows how much reduction you can get in the number of tokens, close to more than 50% reduction in the tokens by using this trick. And then you use that and we train this on this has been trained during Xiaoxin's internship at Facebook, and this took each experiment of those was about a few thousand GPU hours on each 100. At that time, one of the things that has been exciting is that we managed to beat GPT-4V on existing video understanding benchmark, Ego schema, MVBench, MLVU, and decrease the gap to GPT-4o. So this we also show that this model can also perform quite well. This was only 7 billion parameter model. If we use the same mechanism on a 3 billion parameter model, this can also achieve state-of-the-art performance on a smaller size video LLMs. These are some like qualitative examples that shows the model has increased ability to on spatial awareness. So basically, because it has the ability to compress information, and there is also something that I think I didn't mention here. It's called selective feature reduction via cross-modal query. So basically, there are 2 resolutions for every frame. One is lower resolution, one is high resolution, and based on the query itself, the model will upsample the token or lock into like a zoomed-in mode on the frames that are most relevant to the queries. This makes the model more efficient also in grabbing or looking more into the visual information, looking more spatially into the relevant information for the frames that are most relevant to the query. And this makes the model has better ability to understand spatial information in videos. I think I have. Okay, I think there's some technical. Okay. And this is another example that shows that the model has also better ability to understand what happens when the person held the dish, and in this case, after the person was holding the dish, he placed it in the cabinet. Next, I would like to introduce one key. In the next station, I would like to show that introducing structure in the understanding process of video LLMs can improve the performance of both multi-frame and also long video LLMs. The first idea was related to a paper that is appearing at the CVPR called StoryGPT-V, where the idea is basically to generate multimodally every image text pair that construct the story. Imagine that you want to generate a child storybook where every page is a description as well as image that construct the visualization of the story that is going on. And one of the key things that establish a story is the character that you refer to, right? So in order to make a model that works well on this space and can generate also multimodally every image text pairs, we need a model that can perceive multimodal input and also produce multimodal output. This means what? This means that this is, for example, the first 4 prompts for the first 4 pages of the story, and the model we wanted to continue like this. The key idea is based on multimodal fusion of the at the character level, where we embed the visual information of each character as well as the language information, and then we use an LLM mapper to embed these 2 information together so that the model becomes more character aware. So the model is trained on 2 stages. Stage 1 is to train a character aware latent diffusion models, and this is done by basically by image text pairs from this data set, which has text image pairs with characters, and also we have the segmentation mask for every character. So if you think about it, we have now we can compute the cross attention between every token in the text and also every region in the image. And since we know the segmentation mask of the character, you can encourage the model attention, the multimodal model, to have high attention to the intended region of the character, and to have the least attention or do not overlap with other regions in the image. And this is basically this loss, and this makes it more character aware. At this time, this enables a model enables you to introduce a new character. So if you have a new character, you can now feed this instead. All right. Second stage is the integration of this latent diffusion model with LLMs, and this will require us to have an LDM mapper, something that maps the image tokens from here to the character LDM. And another thing is the LLM mapper that takes the images of the stories that has been generated so far and then feed it to the LLM. And this is done by three loss function. One is the LDM like loss, and the second thing is the image generation. How your ability to generate the embeddings of the images that you want to produce, and the third is what we call is an alignment loss. And the idea of this loss is that you want, when you say, for example, they are talking to each other, and this refers to Fred and Wilma are talking to each other. You want they here and Fred and Wilma, you want they to disambiguate into Fred and Wilma. And how do we do that? We have the embeddings of the sentence before disambiguation, after disambiguation. So we compute this character embedding before disambiguation and the words they, and then we make sure that after LLM embeddings, these two embeddings are matching each other. So this is a realization of the idea of how we visually disambiguate like the pronoun here to the characters that we want to refer to. All right, so I can now out of time. All right, so maybe I can refer to this last paper. It's called Vgent. Vgent is a paper that introduced structured into video LLMs. So in contrast to earlier work, we do some construction of a visual knowledge graph, which is extracting entities in the videos. And basically, we merge this entity. And these entities include objects, actions, and so on. And then at this time, we given a question, we retrieve the information based on the entities rather than the frames. So every entities, for example, the same character in Friends series are basically merged into some abstract entity. And then all the visual tokens or the video frames that are related to this character is basically merged into this entity. So basically we do retrieval at the level of knowledge versus the level of the frames. And then with integration of this idea, the model have achieved performance that sometimes beats GPT-4o. And it's also at inference time is much faster. And I think that's basically it. This is just some appellation that shows how naive RAG and graph RAG can introduce like benefit. And I think what I'm trying to say here is that after you retrieve this information, we then ask the model agentically to ask questions for every one of the retrieved videos. So for example, you ask questions like for example, here, for example, you ask question, does the man attempt to walk across the rope, but falls and holds onto the rope? These are reasoning questions, right? And then for each one of those, you ask the question on compared to the relevant on each one of the retrieved clips, and then you have a map of yes, no, and those frames, those clips that have no relevant information are then trimmed, and then we feed this reasoning process to the video LLMs to produce the final answer. I think I would, these are just maybe some benchmarks that we introduced for language reasoning, including chronological understanding, global appearance, character actions, that might be used when running an ICC feed challenge for that. It was the GPT-4 assisted benchmark that has shown that existing models heavily struggle in visual understanding. And it shows that visual information is quite essential. One last thing I would conclude with is we also released recently something called Spooky Pinch, which shows that with signals that with video information that have high signal to noise ratio, existing models have zero performance across the board. So these are tasks that has 98% human accuracy, where existing models struggle to do well there. This has applications in the medical space, for example, and so on. So I think there are some other applications like connecting this with emotions and building emotion aware, integrating audio information to make the models more aware of the tone or the emotion or the culture. I think that's this is a section that I wanted to introduce later, but maybe I can share the slides like later. Thank you.
Thank you, Dr. Mohamed Elhoseiny. Since we're running out of time, we'll take one question from the audience, if any. I see a question on Zoom, if you'd like to. So the question is, do standard video encoding techniques already take into account the static regions, that is background? What about trying to operate directly on the encodings from standard algorithms somehow?
I think the point here is that this background, the point here is how do we separate background information from foreground information? This is something that seems to be clear even from, let's say, Spooky Pinch. Spooky Pinch was basically a noisy image of a word or an object, and you ask VLMs to talk about it. When you pause the videos, it looks like complete noise. Only the motion reveals that there is something there. So existing models does not have a good ability to do that in its current format. So I think the way to do it to manage this, we need models that are more spatially aware, more spatiotemporally aware. And this was the reason why we had to introduce this kind of spatiotemporal compression, which reduced the dominance of those special background information and increased the dominance of the foreground information.
Thank you so much. So, do you want to?
Yeah, sorry, I was actually referring to an earlier part of the talk when he was talking about encoding the information by removing the static background, but it applies to the last part too. So thank you.
Yeah, I think it answers the question. The audience, they just said it answers the question. Yeah, thank you. So let me